Hektoria ended up retreating more than 25 kilometers, and half of that was floating ice, but the other half of that was ice that was touching the ground, which we call grounded ice. And this was the fastest retreat that we've ever seen in the modern satellite record. And if we saw something like that happen on one of these larger glaciers, it could pose a significant risk for rapid sea level rise.
In this ClimateGenn episode, I'm speaking with Dr. Naomi Ochwat about the processes that led to the dramatic and massive collapse of the Hektoria Glacier in West Antarctica. As Naomi says, the research is critical to our understanding of the risk posed by larger glaciers with highly consequential sea level rise potential. Greenhouse gas emissions from burning of fossil fuels and agriculture have irreversibly changed the world as we humans know it. With melting ice sheets and glaciers, sea levels are rising, and a whole host of dangers now confront us all across the planet. This series is about informing and articulating some of the complexities that are often missing in the mainstream discourse, and yet will shape the world in hard and fast ways in the near future. Thank you to all who comment, like and subscribe, and especially to those who are members on YouTube and Patreon. It is greatly appreciated. Thanks again. Naomi, it's great to see you. Can you start with an overview of what your main focus of research has been in Antarctica?
Yeah, thank you for having me. My main focus in Antarctica is to look at the relationship between the glaciers that flow off of the ice sheet and the ocean and sea ice, or the ice that forms from the ocean freezing, and how everything is interconnected and what happens when you change different parts of those systems.
You highlighted a rapid decline of the Hektoria Glacier. Can you tell us what you saw there that was specifically significant?
So in 2022, the area of the Larsen B embayment, which is on the eastern side of the Antarctic Peninsula, it had this sea ice that was fastened to the shoreline, and that sea ice was there for over a decade. And in 2022, it broke away. And what happened next was the glaciers that fed that sea ice area, they started to respond to the loss of that sea ice, and they started thinning and retreating. And what happened at Hektoria was unlike what the other glaciers were experiencing. Hektoria ended up retreating more than 25 kilometers, and half of that was floating ice, but the other half of that was ice that was touching the ground, which we call grounded ice. And this was the fastest retreat that we've ever seen in the modern satellite record.
Can you talk a little bit about the processes that made that happen?
So in certain glacier configurations, the bedrock can play a really strong role in how the glacier responds to such events. You may have heard of like the marine ice sheet instability, which is when you have a glacier that has a reverse slope. So that means that the further upstream in the glacier you go, the deeper the bedrock is. And that allows for very quick grounding line retreat. But at the Hektoria Glacier, what we had was a flat bedrock area. So that means that the slope isn't changing very much as you go upstream. However, what happens then is your glacier becomes very susceptible to thinning. So if you thin a large part of the glacier, that whole region where the glacier's flat could go afloat very rapidly, instead of piece by piece if it was a reverse slope. And at Hektoria, all of the evidence points towards this very flat bedrock zone where the glacier was thinning because of the loss of buttressing from the fast ice. And as it thinned, it started to rapidly go afloat, break up into the sea, and drift away.
In terms of the overall scale, can you just sort of give us an idea of what the change was? When you measured the changes over the last few years, for example, what was the drop-off looking like?
So you lost this fast ice, which was there for 10, 11 years almost. And within the first few months after that event, we lost the floating part of the glacier. Now, this was obvious from the optical imagery. You could see that that part of the glacier, the ice tongue, had these depressions that are indicative of like basal crevassing, and that's cracks coming from the bottom versus surface crevassing, which is cracks from the top.
Yeah.
And what we saw over those first 2 months was giant chunks of the ice tongue just breaking and then drifting off. And then after that, the glacier front stabilized for most of the winter season. And sea ice, like yearly sea ice, came into the area, and the glacier calved a tiny bit, but nothing significant. However, it was thinning. And then in the summertime, if we go to November of 2022, so about 9 months later, the sea ice started to disappear. And what we see happen is the glacier starts to calve. So it's starting to break off. And this time, the way that it's calving is different than the ice tongue. So instead of having these big chunks that are breaking and then drifting, now we have a much more dynamic sort of calving. You see these icebergs that have been rotated. They're much smaller, and you see the bottom side of the glacier. You see that it's turned over. And at this time, we saw 8 kilometers of the glacier retreat in just a 2 month period. And that was when I was looking at the data, I was thinking this is something spectacular because we've never seen it before. And then it started to stabilize at a new terminus position and thin even more rapidly. So it's the glacier's still thinning and calving into the sea, just the front of it isn't moving back. And the study ended in 2023, and since then, there have been other periods where the glacier has calved a bit more, but it's not this 2 month period where we lost another large chunk of the glacier into the ocean.
That seems quite an interesting point because in terms of what you see this dramatic change, and you said it's a sort of spectacular when you see it. Is it a step change in the trajectory of warming, or do you see the potential sort of countervailing forces that could create a bounce back?
A bounce back to the glacier.
Well, to sort of the glacier reforming. I'm assuming the answer to that is no, but I just wanted to in case I was missing something.
No, so there's no way the glacier could reform anytime soon. We would have to be on a very different climate trajectory in order for it to regain the mass that it's lost. Because, for example, it was thinning at over 80 meters per year, which, I mean, you would have to then input 80 meters of ice per year in order for it to start to equilibrate. But in terms of a geologic cycle, if we just ignore climate change for a moment, it's not impossible for the glacier to form at any point in the future, just not with our current climate predicament.
We hear a lot more about the sort of Thwaites and the Pine Island Glacier, these ones that are very consequential for sea level rise. How do you connect the importance of the Hektoria Glacier collapsing to these sort of larger scale risks?
So the Antarctic Peninsula is changing a lot faster than other areas of Antarctica, such as the Amundsen Sea region. And it kind of serves as a natural laboratory for seeing what processes can happen glaciologically. So, for example, in 2002, the Larsen B ice shelf broke up via hydrofracture and like melt ponding. And then those melt ponds crack through the ice and caused this very large ice shelf to break away. And what we're seeing at the Larsen B area now is another representation of processes that could occur in other areas of Antarctica. So Hektoria itself is a relatively small glacier by Antarctic standards. It's not like Thwaites or Pine Island. It's tiny compared to them. But this ice plane process, where the ice plane was conducive to this rapid thinning and then lift off, essentially, which then further destabilized the glacier, right? So Hektoria lost the floating ice tongue, it lost the ice plain region. And because of that, the whole glacier has deflated and continued to calve and retreat. And if we saw something like that happen on one of these larger glaciers, it could pose a significant risk for rapid sea level rise. We need to study that more because this is the first indication of this process happening in the modern record. There was a study that looked at the paleoglaciological record, and they found that it happened in the past. And now we just need to know if there are other areas that would be susceptible to this sort of rapid change.
We know that we're going into a hotter year. We're seeing the impacts of climate change all around us now in a sort of material way. These are consequential things going on in far off places. How much do you continue to monitor them with your colleagues?
We're constantly monitoring things. So there's this really nifty resource that's open for everyone called Worldview MODIS imagery. And there's these satellites that circle the globe every day and take pictures. And we are always looking at different hotspots kind of around Antarctica to see what changes may be happening, such as melt. So we're looking for melt ponds in different areas, and then for indications of rifting or breakup of different ice shelves. So I'm involved with the International Thwaites Glacier collaboration on the Tarzan team, and we're looking at the Thwaites Eastern Ice Shelf every single day to see, has the ice shelf broken up? What's happening to the sea ice in the area? Because the sea ice can play a role in that. And when's it going to happen?
What
What's going to happen?
When you say it like that, and we're looking at it every day. I mean, the last on the coast near where I am here, the erosion in the last couple of years has been absolutely fantastic in terms of what you're talking about is a different thing. If you're talking about things like the Thwaites Glacier and you're looking at you make it sound like something, not that it's imminent, but there are changes. This is happening in real time, and we need to be more aware and care more about what's going on in places like Antarctica.
Exactly. It is happening in real time. And that's how I learned what happened at Hektoria and the importance of the process, right? Because if I was only looking at Hektoria Glacier once a month or once every 4 months, that retreat rate wouldn't have been captured. It may have not looked like it was anything spectacular if I was checking every 6 months or 4 months, because I would have seen a point in time and saw that it retreated, but I wouldn't have seen how quickly it retreated. Where I remember with Hektoria, there was 3 days where it retreated 2.5 kilometers. And if I hadn't checked those images that regularly, I wouldn't have seen that happen. And that's what we're doing with the Thwaites ice shelf as well. And I mean, I'm continuing to monitor Hektoria and other areas like Crane Glacier in the southern part of the Larsen B to see if changes are happening.
With the Hectoria, when you talked about the sort of flat plane of the bedrock and how that provided a certain condition, how many of these other larger scale glaciers have a similar sort of setup to that?
That is a really great question, and one that I'm hoping to do more research on because we don't know. We have some bedrock data in some areas of Antarctica, but it's very difficult to assess along the coast what the bedrock is like along the entire coast because you really need radar, like airborne radar data. And that's this tiny little swath of data that most of Antarctica doesn't have, for example. In some places you do, like at Thwaites, we do have, I think there's been several field campaigns that have gotten bedrock data from seismics and radar. And so there's certain areas that we have more information on, but for the vast majority of Antarctica, we don't have in situ data. We have some models that model the bedrock using ice velocity, and it's better than nothing. And we still need in situ data to know more about the bedrock.
Okay, so if you do find that these conditions are replicated in other places, this becomes highly relevant in terms of understanding what, well, is likely to happen in terms of the process.
Exactly. And it's not just where these conditions are, but where these conditions may be susceptible. So, for example, there was an ice plain on the Ross ice shelf, but the Ross ice shelf is the size of France. We're not really worried about the Ross ice shelf breaking up anytime soon. And so the presence of an ice plain there isn't that concerning in a way, right? But if there's an ice plain on the Getz ice shelf, or if there's one on Pine Island that's close to the coastline, then it's maybe something we need to look into more. So it's like the prevalence of the ice plains and whether or not they may be susceptible to rapid flotation.
Just to end on, last year I went to two conferences on climate interventions, and I was curious because there were people there, climate scientists, glaciologists, and people I wouldn't expect to see at these conferences. And I wonder what your thoughts are about interventions, given that you're up close with these giant climate systems. When you look at that, do you think, oh, we could we could do something here?
In my opinion, I think that the majority of climate interventions are a huge risk and a detraction away from solutions that we know already work, and a huge waste of money on resources and research time for the people that are studying them. I think that carbon capture and storage, as in terms of a intervention, is an important route that we should be pursuing, because I do think in terms of geoengineering that carbon capture and storage will be necessary and is worth the investment in researching it. However, if you're referring to the sea curtain or pumping the water out from the base of the ice sheet, um, yes, how do I put this? I think it could be detrimental to actual progress. And I think of it in terms of how much time we have to research these things. And we have a large glaciological community, but it's not that large, right? It's, I don't know, a couple thousand people. And our time is highly valuable. And I think we should be spending our time researching fundamental questions about glaciers and the processes that could be occurring, and looking into the future in terms of the trajectory that we're on. And I think spending that time researching, I don't know, a sea ice curtain could be problematic, and it can detract the public and the policymakers from actually doing something, which we know works, right? We know if we reduce our emissions.
So you think that it's not really viable in terms of in the time frame we have, the resources and so on?
Absolutely not. I mean, I know how long it took me to get to Thwaites Glacier and the resources that it required to send a team of 8 onto the ice shelf, and how long we were able to stay on the ice shelf. And that's 8 people for a 2-month field season. And the resources that would be required for any of those climate interventions are exorbitant, especially compared to what's down there. And in a lot of those cases, with the different interventions, you would spend more carbon getting there or setting up equipment there than it would in reducing any kind of the impacts.
Okay, no, that's fair enough. That's a good reply. Thank you very much. It's been really cool to speak to you and learn more.
Nice to meet you, and have a great day.
If you are concerned about the future, then why not travel with me through every COP conference from COP21 in Paris to COP28 in Dubai by ordering my book COP Out: How Governments Have Failed the People on Climate. In COP Out, you'll gain insights into what is actually going on in these supposed world-saving conferences and how we have ended up in this dire era of dangerous consequences. You can order COP Out via the link in the notes or on any online bookstore worldwide in paperback or audio version.